Okay, so welcome back. Now we are actually into the spatial operations, and we already discussed the basics, the most important mathematical definition of a spatial operation in terms of convolution. And now let's actually explore. Okay, so one of the beautiful applications, as I said in the last class, is spatial filtering. Okay, so you might have heard about, if you're coming from again as a signal processing background, you might have heard about many of them in 1D perspective. So here we talk about in the 2D perspective. Okay, so spatial filter kernels, again, you can call spatial kernels, but filter has a different meaning to it, right? So let's call it as spatial filter kernels. Okay, so they are designed, in variety of applications, right? So always you design a spatial kernel based on an application. So for example, based on your mathematical intuition, if you want to do averaging, you know what sort of a kernel you should use. So what sort of a kernel you should use? Can somebody tell? Can somebody just think about it? What sort of a kernel? Okay, so I can put it. Okay, so what I want, just remember the definition of convolution. Dot product, sum it up. So if I want averaging, I can go for a kernel like this 1, 1, 1, 1, 1, 1, 1. So basically, sort of adding up all the neighborhood, okay, all the pixels in the image, and of course averaging you need to normalize, right? So this is totally 9 here, so 1 by 9 into this, or as simple as that, basically 1 by 9, 1 by 9, 1 by 9 throughout. Okay, so that is the concept. So that is averaging. So I get the kernel in that perspective, right? Okay, so let me raise. Okay, and it can be differencing. So let's say I want to enhance edges in an image. So how shall I go about it? Okay, so we'll talk about this, and then something which is very non-linear. Okay, so there are problems with averaging. For example, if I average, as we saw in many cases, it will have a smoothing effect, right? It will smooth the edges. The edges will become really blurred. Okay, so I'll have examples, so you don't have to worry. In that case, we may have to move and become more clever and come up with something like a median filter. Okay, so those are interesting. We'll see that. Okay, and then it can be even from something like you define a space. So just now I showed you an averaging, but the problem with averaging is like all pixels are having equal weight, right? So let me just put it back again. Okay, so in the case of averaging, I had equal weights for all the things, but I may think that, okay, I am going to replace this guy, so why should I give more weights its neighbors? So in that case, I can come up with a kernel which is actually something like this. I'm just putting some number, okay? So 2 here, so 1, 1, 1, 1, 1, 1, 1, 1 here. And then of course this will be like 3 plus 3, this will be like 8 plus 2, 10, so it will be 1 by 10 normalized, and here it is 1 by 9 normalized. So what you are doing over here is weighting the center pixel more. Okay, so this is what you are trying to, this is how you can play. It's a beauty about the design. Okay, and see Gaussian here. Okay, so Gaussian has an interesting property, right? It is peaky at the center, and then it has sort of isotropic diffusion. It has an isotropic loss. So imagine a Gaussian. It has a peak at the center, and then in all directions, okay, in east, west, northeast, northwest, all directions, the decay is the same. Okay, so that is a beauty about Gaussian. Okay, so you can have a Gaussian window instead of a Gaussian kernel instead of a rectangular kernel like this, or even this is also something like a weighted averaging, right? So all these are possible, and we will talk about frequency function in the next lecture, maybe next week, where we talk about transformations. Okay. When we represent image in a different domain altogether, then you can define filter in that domain. Okay, so you take the image to a different domain, you do filtering there, then you take the inverse transform and come back to the spatial. Okay, come back to the XY coordinate. Okay, so that we will discuss in the next lecture or next week actually. Okay, and then remove all this, all the ink. Okay, then as I said, these two are related, so I can define a specific basically response, and even in that domain I can actually have an orientation. Okay, I should only target a certain orientation removal, for example. Okay, so that and all is possible. This, for example, just to give you an intuition, you might have heard about fingerprint biometrics, right? So fingerprint has a particular pattern. If you see fingerprints, it will have a particular contour sort of pattern, right? So then directionality of the filter is extremely important. I am going to basically keep only a certain direction, everything else actually I am going to remove from the image. So all these are possible, okay? So that's interesting. So we'll have some examples that will make it very clear to you, okay? So far you just need to understand that spatial filtering, it can be done based on intuition, mathematical intuition, like what operation you want to do, whether you want to smooth or average an image, whether you want to enhance the edges in the image. If the image is having lot of nonlinear noise, then you may have to do something. And it can be even in a certain domain, you represent the image in a certain domain and do filtering there. Okay, so all these are possible. So now let's actually do in a more official way. Let's characterize, okay, the concept. Okay, so spatial filtering can be linear or non-linear. Okay, so this is very important because when we say linear operator, a linear system, then there is a possibility that you could recover the original image. There is always a possibility that you could recover the image. But when we say linear filtering, it's not like that, right? Because, for example, smoothing, you will actually sort of average the entire image. But then when we say linear, there is nothing but the operation is linear, because let's say 3x3 kernel, you are doing an operation. The 3x3 kernel will move to the next location after a stride, but the operation is remaining same. So you're doing averaging in both the cases. So it's a linear operation. So throughout the image, you are applying a linear operation. But let's say we'll talk about this beautiful filter, median filter. Okay, so then you understand what you mean by a non-linear operation. Okay, so non-linear simply means in each of the windows, let's say first stride and second stride, you are doing the same operation, but the result is not the same. Okay, result is purely dependent on the data, the intensity values in the image. In that case, the image is, the operation is becoming non-linear. Okay, so we'll discuss that. If you don't understand that, forget, don't worry. Okay, so the filters, as I said, can be linear and non-linear filters, and within the linear filter itself, we call it smoothing. For example, here, this is a moon image, and this is a smooth image of the moon. You can see that all these high noise things are getting smoothed, and image starts to look blurry, right? So maybe I'll just zoom in for you just to get a feel. Okay, so you can see it very clearly. Many of these drastic, small, rapid changes in intensity got smooth. Even this boundary, if you see, it gets smoothened. Okay. And then the other way is sharpening. It is just the opposite of smoothing. So for example, here, in this case, I'm just doing the sharpening. Sorry for that. Yeah. So if you see over here, you nicely captured the edges, right? And many of the high varying patterns. So I think in one of the assignments, you had a histogram representation for such an operation, right? So exactly similar. So it is like edge enhancement. So you are identifying the edges of the moon and more of the high intensity variations in the image. You can do sharpening. And then you have somewhere in between where I don't want to really smooth or really enhance edges, somewhere in between, which is the band pass operation. Okay, so let's concentrate on smoothing. Okay. One of the classical application is the removal of high frequency noise or rapid changes in the image. I don't want to have rapid changes in the image. I will use the smoothing operation. And another interesting application is the anti-aliasing filter. Okay, so this is something which is very important. We will discuss that at a later point of time. So that time we will have a detailed explanation of what exactly it means. Then false contours. Remember the contouring effect in quantization. You can make it smoother by using a filter, right? A smoothing filter, right? If you apply on a image which has sort of blocky or the contour artifact, you smooth it. Okay, as simple as that. So some of the this we already saw it. So what is the kernel for a smoothing operation? So this is what we saw it. So this is a simple averaging. So if you want to treat this, okay, if you want to consider this is in a surf space or a 3D space, it looks like a box, right? It will be like 1, 1, 1 and sudden jump. It's like a rectangle in 2D and it's like a box in the case of a 3D space, right? So just imagine that, okay? So, and this operation is important because otherwise your image intensity will be different. Just to normalize this operation is extremely important, and that's why it's called average, right? Okay, and then as I said, there is no need to have equal weights. You can control the weight. So here is an example of a weighted average filter, and then here is a Gaussian filter. Okay, So this means the sender will be having the highest intensity and then sort of gradual decrease in all directions. So here you could argue me that there is this slope is slightly low, higher compared to this slope. So it is not really isotropic. Okay, it is actually it all based on your sigma, right? The spread. Okay, so in this case it is a Gaussian operation, and if you remember the Gaussian expression, I hope all of you remember that from one of our hands-on exercises in the maybe first lecture. So you can create a Gaussian, and Gaussian you have control on the center of the Gaussian and on the spread of the Gaussian, right? So you can actually create it in row direction, column direction, and everything is in your control. Okay. So now let's actually see an example. Okay. So this is a cameraman image. If I apply a box filter on the cameraman image, you have this. If I apply a weighted average, you have this. And if you apply a Gaussian, you have this. Let's zoom in and see what are the effects that you're seeing. Okay. So this is the image, and obviously you see the graphs which has a lot of intensity variation. It's completely gone here. Okay. And let's compare these two. Okay. So if you see over here, this is more blurred compared to this, right? The intensity is much more evident in this image compared to this. That is because you are weighting it more. The center pixel is weighted more. Okay. And this is the most interesting aspect. Okay. So this for example, it's very interesting to see that maybe it's not very evident from any of these. Okay. But I have a very interesting chart in the next slide which makes it very evident, okay, for you. Okay, so let's go there, I think, rather than spending time in this chart. Okay, this is the example. So this is an original image. Okay, so if I use a box filter, I have something like this. If I have a Gaussian filter, I have something like this. So you see, let's compare actually the Gaussian and the box filter. Okay, so you see this pattern and these edges. Okay, and here, for example, these artifacts. They are all smoothened, like much more smoother compared to this guy. So that is the biggest. So you can see over here also these patterns are much smoother in the case of a Gaussian. Okay, even this will be much smoother than the box filter. Okay, so Gaussian is sort of it's like a smoother increase. Like think of a Gaussian, it is like maybe I'll just represent it here. So box filter, if you see a response, it is something like this, right? In 1D space. Gaussian is something like much more smooth, right? The gradual, right? So since this is smooth, this part is very rigid. That is why you see the blocky artifacts in the final image. Okay. So this is the application of filter, and smoothing is actually quite common. You might have done it even without knowing all this, right? And I just want to go back to this case. So a filter is as simple as design of the kernel. So when I say this is the kernel, immediately after observing the kernel itself, you should be able to tell me that this is doing smoothing, right? It's very easy to explain that. Okay, now let's actually take an interesting application. I am very sure you might be aware of this particular example, right? This is part of assignment 1. But don't use this because you have not studied this if you want to solve assignment 1. Assignment 1 is purely using addition, subtraction, and point operations. Okay, you can't use this. Okay, so if somebody uses, they won't get any credit. So we have an image here, and as we can see, it's very evident that there is a gradual increase in intensity from left to right, in this direction. So all I need to do to improve this image is to compensate for that. So basically nullify this gradual increase. So improve. So I just need to invert, invert this trend. So how shall I go about it? So here what I did is, there are many ways to go about it, but here what I did is, I heavily Gaussian filtered. So when I say heavily Gaussian filtered, I increase the kernel size, okay? Rather than 3 by 3, I can increase it to 5 by 5, 11 by 11, you can play with it. And then if I do a heavy filtering on this, heavy smoothing on this, I end up in getting a image which is output image, which is like this. And this sort of captures the intensity trend in this image. So this image sort of captures the intensity trend in this image. Once I have the intensity trend in this image, all I need to do is just divide by that, divide the original image by this intensity trend. I will reverse it, and that's what you're seeing over here. Okay, so this is very interesting, right? So I had a very bad image. All I did is, from the visual inspection, I understand that there is an intensity issue here. So I've estimated that intensity and divide this intensity Okay, from this image I get the original. You see you can even see the internal structures getting visible, for example. But of course it's not really perfect because some of these regions are getting saturated. But still, it's much better. If you compare these two images, this guy is terrific. I mean, very good, right? So that's what. So a very classical example. I'm sure you will be, appreciating this, right? This operation. Okay. So in a nutshell, basically the smoothing operation is nothing but you design a kernel, design a filter. You can design an averaging filter. We call it as box filter. You can have a weighted average. You can have something like a Gaussian, and you just play with it. Okay. So typically, if really you don't care about designing, you always go for Gaussian because that is the best bet. Okay. Now another, this is very important. Okay. So before moving, to this filter, okay. So I want to maybe stop with a very interesting derivation. So we will come back to median in the next lecture. Okay. So before moving to the median filter, let's actually spend some time in understanding an interesting concept behind the averaging filter. Okay. So this will be definitely interesting for you. Okay. So I'll put maybe a statement across to you and let's prove that. Okay. So the statement that I'm going to put is, so what operation that we are going to do in a filter. Okay. So this is an image, right? And let's consider only that 3x3 case, which is a easier way to explain. So these are 3x3 pixels in an image. So what I'm actually doing is I'm going to replace this guy by a value, right? So by some value. Okay. So let's call this as A1, A2, A3, A4, A5, A6, A7, A8, A9. Okay. So these are the, let's say the intensity values in these 3x3 locations. So what I'm actually going to do is replace this guy A5. Okay. So A5 guy. So this A5 guy will be replaced by some value. That is the operation I'm going to do. So my question to you is, what operation sort of minimizes, or what value should be the A5 value which will minimize the error, the least square error between each of these neighbors, okay, and this guy. Okay. So because we are trying to represent this guy in terms of its neighbors. That is our objective, right? So we want to replace this A5 by some value. Let's call it as A5 dash, right? So what value of A5 dash will give me least square error? That is, if I do A5 dash minus A1 square plus A5 dash minus A2 square plus etc. All of them, including the self, A5 minus A5 is 0, so don't have to consider. So what will be minimizing this value? Okay. So this particular operation. So that means I'm going to substitute A5 with some A5 dash, which will minimize the error between all of these. So let's find that out, and the answer is very interesting. Okay. You might, somebody, very familiar with this already might be knowing it. Okay. But let's do that. Okay. Okay, so I just derived for you actually because I don't want to spend a lot of time in this. So this is again, I'm just trying to reproduce. So A1, A2, A3, all the values are here. So what the essential operation that we are going to do is, right, in any spatial operation that we are going to do is basically replace that sender pixel A5 with some value AC. Okay, so now my question to you was, what is that value of AC which minimizes the error, the least square error between each of, or mean square error, not least square, I should not call that, mean square error between each pixel to its neighbors. So this expression, right, in this case you have 9 pixels. So AC minus AI square, all AI is basically, so AC minus A1 square plus AC minus A2 square and so on. Some value of AC, I want to find that, okay. So which minimizes, so this is the mean square error basically. So this value, new value AC, which minimizes the error to all its neighbors. Okay, so basically find out the error, the square error, mean it, and you have the mean square error. So I want to actually find out that value AC, which minimizes this expression. Okay, so as usual, what you need to do is, what you do to find the minimum, you differentiate this with respect to AC and equate it to 0. Okay, so in this case, if I differentiate it, it will become 2 by 9. Okay, 2 by 9 here, and then AC minus AI, and this factor will become 1. So this is the differentiation. So basically, you differentiate MSE with AC and equate it to 0. You get this factor, and this 2 by 9 you can ignore it, and this AC now can be brought out because it is not dependent on I. So this becomes AC minus sigma I equal to 1 to n AI, right? This is a factor. And you put this out, this to the other side. So what is the value of AC? And this is very, very interesting, right? So AC is equal to sigma I equal to 1 to 9 AI. Wow, that means the value which minimizes, okay, the mean square error between that value and its neighborhood has nicely come out as the mean of that particular, or the average operation of that particular pixel, right? So that's what you are actually arriving at. So that's the importance of the mean filter or the average filter. So average filter is the filter which minimizes the mean square error between the new intensity value and all the earlier pixels. I hope I'm not confusing you. If you are really not understood this, just ignore it, no problem. But always keep in mind, okay, this question can come, right? I'm doing a spatial operation. I'm doing sort of a replacement operation, right? I'm going to replace this pixel basically by a new pixel. So what is the best bet for me so that the error between this new intensity and these earlier neighborhoods, including that pixel, is minimum. And if you do the derivation, you find that it is nothing but the average value. Okay? With that, we'll stop today's this lecture, and we will start with something known as the median filter. Okay? So the median filter, we will discuss it in the next class. Okay? Till then, bye.